In this presentation, I'll provide a basic and short introduction to Bayesian Evidential Learning, which can be seen as a scientific protocol for uncertainty quantification. The context for Bayesian Evidential Learning and this protocol comes from a publication in A.G. Wiley, Quantifying Uncertainty on Subsurface Systems. So in this book, we're looking at Earth resources in general and how we will explore for them and exploit them in a sustainable fashion. Often what we have to deal with in such exploration or exploitation is resources environment. Obviously, we want to extract the materials, water or energy from the subsurface. At the same time, we have to be guarded in terms of its impact for the environment. So it's a risk versus return question that needs to be addressed, and decision making needs to be optimal under such circumstances. So within this broader context of quite complex decision-making under uncertainty problems, the paradigm that has been evolved from various case studies is this Bayesian Evidential Learning. So there are obviously three words in this, and the first one is Bayesianism, which means that it will rely on the fundamental notion of prior understanding and the contribution of Bayes in that sense. Bayesianism is not necessarily a method, it's a way of reasoning and a way of understanding what we know about knowledge or what we know about uncertainty or not. And so it's evolving essentially as an inductive-deductive form of reasoning about science that can have its applications in uncertainty quantification. Of course, central to any uncertainty quantification is data, which here will be more broadly determined as evidence. In terms of making it all happen in a very efficient and manageable fashion for real forecasting problems, which have often complex models, various sources of data, difficult to manage for models and forecasting models, it relies simply on Monte Carlo. And therefore, it will be considered to be a learning method rather than an inversion method. There are 6 stages in decision-making under uncertainty when we are dealing with Bayesian Evidential Learning. And it's very important to keep this protocol as is and sort of not try to put one step in front of the other. The reason for that is that going through this protocol will follow a certain logic that will make certain that at the very end we have an uncertainty quantification that makes scientific sense and that can be applied to a specific decision problem. As such, the first step in Bayesian Evidential Learning would be to formulate the decision question and state the very important prediction variables or the key prediction variables. Then secondly comes the Bayesian part, which is we have to state what is called prior uncertainty, which means that in all of the modeling we're going to do, there is already some information available about what we have. If no information is available, then typically we would take uniform distributions. But often I would say that we shouldn't go directly to such uniform distributions. We can deal with distributions that are obtained from set analog information. This statement of prior uncertainty is just a hypothesis. And here often we don't need to be very accurate because the next step we're going to go through a falsification step. That is, we're going to try to disprove this prior uncertainty model with observations. And so this involves doing a Monte Carlo and running basically a Monte Carlo experiment. And after the Monte Carlo experiment, we'll do some kind of statistical falsification. What's critical about the falsification is it doesn't require matching any data. It's just kind of making comparisons between statistics that are generated in the Monte Carlo and the statistics that we have available in the observations. In order to do the uncertainty quantification, we need to have a better understanding about sensitivity analysis. In particular, we like to understand what in the models is most impacting my predictions. And having that understanding, of course, I like then to know what observations are most important in reducing those important variables. So we notice that here we don't take for the first step where we start immediately doing inverse modeling, but we first ask ourselves the question, what is it that we really need to know? Because in reality, of course, we have many uncertainties, can be hundreds of parameters. And so dealing with all these parameters in inverse modeling becomes an impossible feat. And so this is why the sensitivity analysis becomes so important. Then finally, and this you see is a step that comes pretty late, is that we will do an uncertainty reduction of these prediction variables based on information. And so this could be seen as the classical inverse problem. However, we will not use the classical inverse methods. Instead, as I mentioned before, we will be using Monte Carlo and learning from Monte Carlo in order to avoid doing many complex iterations of the problem. Once that is done, we can now make a decision, but also, more importantly, we can falsify our uncertainty quantification. This is also an important step. There are methods for doing such falsification that allow us to verify whether or not the procedures that we have run actually led to something that is meaningful. We can also try to understand a posteriori what is the sensitivity, what are important variables that were eventually going into this decision making. The point of this presentation is not to go through deep into case studies, but just to provide you with a flavor of what these various steps are and how we can visualize them. In the book and in other publications, there are many applications of this, and so here is one of those applications that you also find in other YouTube videos, as well as fully described in the book. So here we're in Denmark, and in Denmark we're looking at a particular water management problem. Specifically in Denmark, we have issues related to drinking water production that leads to draining of rivers and wetlands, as well as possible industrial and farming pollution. So in order to mitigate the effect of this, we like to optimally place the location of drinking water wells. So that's what we see here, is that here is Denmark near the city of Aarhus. And so we'd like to place the well at location A, B, C, or D. So the choice of the decision problem is very simple. Where do I drill the next well? This problem is not simple simply because in Denmark we have a subsurface that consists of glaciated valleys, and this shows up, for example, in TEM geophysical data acquired that shows these high resistivity areas that are these buried valleys. So the subsurface is very complex and heterogeneous, so placing these wells at various locations is not a simple problem. In addition, we have various other sources of information, such as from boreholes or hydraulic head observations. Formulating a decision question is simply stating what problem do I exactly want to address. And the problem I want to address is not building the model or quantifying uncertainty. The problem is making a decision between A, B, C, or D. And what would it take to solve it? So what would it take to solve it? Well, the first thing in a decision on uncertainty is that I need to make some decision objectives. So obviously the decision objective here is to get this drinking water out. And to do that, I need to drill the well in a location such that I minimize the drawdown. Obviously, we don't want to drill wells in low hydraulic connectivity areas. However, the problem of drilling wells in certain location may have an effect on stream flows, and wetlands, which is these two. So we want to make sure that we minimize that effect, or here is maximize the reduction potential if I take my well and put it in a different location. And also we want to minimize risk of contamination of the drinking water, which could be due to particularly farming and industrial pollution. So basically now I can make new important prediction variables, which are here for drawdown. I have a prediction variable. This is a prediction variable have to do with the stream flow reduction potential, wetlands reduction potential, and industrial pollution and farming pollution. Here they're simply scalars, but in reality they could also be functions of maps. So here's then what I need to get to. I need to get to this point where for each location and for each objective I have a certain score, such that later on I can use these various scores in order to come up to a single score on which I can then make a decision of where to drill. So how do I get these various scores? So now we've clearly defined the objective, clearly defined the decision problem, and so our uncertainty quantification problem gets more meaning and also gets more purpose. The second stage is perhaps a difficult stage for most of us, since it's something that we typically don't do explicitly. And that would be the statement of model complexity and prior uncertainty. In other words, I have to now go to a design problem. This design problem is partly conceptual and partly mathematical. So what we have to do now is to conceptualize Earth. So in the Danish groundwater situation now, I have to not start working with data, but I've started more thinking about how would I represent Earth. Representing Earth in a mathematical sense will simply be stating various model parameters. And there's a lot of choices and subjectivity. One may opt for a very complex model, one may opt to leave out certain model components or build in certain model components, and so on. The second part of that then is once I have defined important model components, such as, say, the amount of faults, the mean hydraulic conductivity, then I can state prior uncertainty. And here, on prior uncertainty, we don't need to necessarily be very accurate. In terms of the prior uncertainty, we need to essentially go and look, well, what do you already know and what is not known? And this could be very broad. This could be broadly about what does the community know about this, or in this particular site, what I already know about it and what I don't know about this. And so this, again, is a very subjective exercise. So, for example, for the faults, for prior uncertainty number of faults, we could say, well, I have a Poisson distribution with some certain mean amount of faults. And so that would be then this prior uncertainty. But it, of course, can be much more complex. It could also relate to a particular epistemic uncertainty related to a physical model, and I don't know which physical model I should be using, so I use a variety of them and I state some prior uncertainties on them. So that's what that really means, is we define the model complexity, which is the model parameterization, and once we have that, we define the uncertainty on it. We also notice that we're not going to cut everything up into pieces. We're not going to say I'm doing it separately for all the pieces that are there. I need to do this jointly, and that may involve many fields of science, particularly when we're dealing with the subsurface. We may need to deal with sedimentological parameters, structural parameters, rock physics parameters, etc., all the way up to engineering parameters. It's important to understand at this point we don't need to be accurate. We're just making a hypothesis, and this is how we should see it. Because in the next step, we're going to do a falsification. That means we want to test our hypothesis with certain statistics and certain statistical exercise. And so we may falsify the model, and so we have to come back to revisit possibly the complexity as well as the prior uncertainty. Here's an example of how we did that for, or how this was done for a very large oil reservoir in Austria, which is called the Madsen field. And so in the Madsen field, we notice that we have 6 years of already production, and so people wanted to enhance production through polymer injection. So in order to do that, there's many variables that are going to building a reservoir model. So these are geological and geophysical variables. These are flow and transport variables. And so what we're doing is we're not just treating first the geological and geophysical variables and then later on the flow transport variables, but we're saying we need to address all sources of uncertainty jointly. And this is very important. It looks then like this is going to be an impossible exercise, but this is actually not the case. It's actually the case that by considering all variables jointly, that it becomes a very possible exercise. If we will be dealing with several variables separately, then the exercise actually becomes very difficult. So when we deal with, for example, the Danish case, we come to a table. And so I highly recommend making tables like these, just to be very explicit about what is being done. And so in this table, we may have various fields of study. For example, I may have fields of study related to deglaciation, fields of study related to hydrogeology, hydrology, river science, etc. So all of these boxes are individual modeling components, which could be from various elements of science. And so you may end up with many parameters. Then comes Monte Carlo. So once we have done all this, we can simply now run a Monte Carlo. And central to the Monte Carlo is to start with this M on F of M and to draw many models or many model realizations. So this could be leading to rather high-dimensional models, could be spatial models, gridded models, whatever you have in that case. Then we have to define a forward model. This is basically our conceptual representation of Earth as we see it. We'll come now next are actions that are done by humans. For example, gathering data from Earth is an action done by humans, and so that can be modeled using a data forward model, which results then in the data variables. So the data variables are not the observation; it's just our physical representation of how models are transformed into data variables. So these are basically also variables. Then we also have the observations. These are the actual measurements. So you could say this is the past, this is what we are measuring and have measured, and this is the future. So I'd like to also make a prediction. So that would be the prediction forward model. For example, I predict the amount of pollution generated by pumping at a certain location. That would be the prediction variables. And so I would have here this prediction variable, which I'll call H. So we just do straight Monte Carlo. We have many other forms of Monte Carlo, Latin hypercube sampling, etc. These are all just form of Monte Carlo. The point is to do a Monte Carlo, simply because in uncertainty quantification for complex linear systems, there's no other way to get there through Monte Carlo. In Monte Carlo, we are then generating indeed a lot of information. If you look at the Austrian field, we're looking at building sedimentological models, lithological models, porosity, permeability models, engineering models, etc. So this leads to generating a whole lot of information. On that, we then apply for models. So in case, for example, of reservoir forecasting, we have already existing production data. So what we're doing is running flow simulations to predict or to essentially create for each model the data variables, which we are the variables DL here. And so that's what we see here in these gray curves. So we have many wells where we have simulated production data, and we have also our red curve, which is the actual observations. Then on the other side, we'd like to, for example, know what is going to be the future field oil rate or water rate, or we would like to understand it per each well, or we'd like to understand how much oil is left, or we have some kind of key prediction variable. So the question now is how we're going to represent all this complex information. And so fundamental to that is going to be dimension reduction. And there are many dimension reduction methods. But all of these dimension reduction methods, in my view, are sort of variations on the same theme. Is that imagine you have a very complex variable x, which is a vector. And so in one of the fundamental applications of dimension reduction, we're going to represent this, this vector as a linear combination of basic vectors. So the idea is that these basic vectors are some kind of a geometric representation of this vector, and these linear combinations are essentially something that represent variance. So we're going to decompose our complicated model into something that has a scalar and that represents variance, and something that represents the geometric shape in very high dimensions. And so notice here that I can do that on whatever x that I have. And so in our case, that x could be our data variable, our prediction variable, our model variable, whatever that we have. So here's an example. Suppose I have a complex 2D model here. It's not necessarily complex, but something of a high dimension, say thousands and thousands of variables, which is equal to the number of grid cells. What I can do is, if I understand these basic shapes, which are fixed, I can write this model as a linear combination, essentially, of these eigenfrequencies. For example, principal component analysis is a method that would do that. Principal component analysis generates me these fixed basic shapes, which are now called eigenvectors, and these eigenvectors are independent, means that their transpose times that one will be equal to 0, and the transport with itself is equal to 1. And so doing that, you notice now I decompose the problem into potentially simpler problems, because essentially I can keep these fixed and then these are varying. And so these are called then the scores. When you talk about any other method that are more difficult, or more advanced, such as kernel principal component analysis or nonlinear principal component analysis or deep learning methods, essentially they end up using the same ideas. Eventually you end up with some shapes and some scores which are representing variance. So I can then plot these scores into a score plot. So if I do that, then each dot would be a particular model that I generated, and the score attached to it. The shapes, remember, are fixed, the scores are varying, and so now I see the variation of high dimensional models in a low dimensional representation. Okay, let's do that for another example that we have in the book, which is an example related to uranium contamination in the United States. So there we have a problem of contamination that needs to be bioremediated, and so to do that, people inject chemicals in the subsurface that activates biological reactions, and that therefore precipitates the uranium or reduces uranium from uranium-6 to uranium-4. In order to do that, we have to evaluate essentially the efficacy of that action, and to do that, we run reactive transport models. So here we see, for example, we have an area in Colorado where we inject acetate, and if you run a forward model, we see that we get concentrations of uranium that are being precipitated. And in some cases, that seems to work not very well. In other cases, that seems to work rather well. So we'd like to understand, are we in this case or are we in that case? To do that, we have to build a prior model. So again, we come to this table. There's a lot to say about that. This could be done from observations, from analog sites, from already understanding about what has been done before, etc. But in this case, we have a series of uncertainties that are both geological as well as reaction rates, which are geochemical or, for example, mineral surface area, etc. Once we have that, we can run a code called crunchflow and generate many reactive transport models that give for all the boundary conditions, geochemical conditions, geological conditions, provide you these model realizations. So if we now use principal component analysis, then I can take any of those models and reconstruct and reduce dimension on those. So for example, if this was my resulting uranium concentration model, then I would need about 300, I would say about 100 principal components to represent that with some reasonable accuracy. But that's already nice. We have potentially a large image here that is now reduced in dimension to 100. Now, when we have done Monte Carlo, comes an important step, and that's called falsification. So what we now do with all this information is, in particular with the data information, is we take our data variables, we run these dimension reduction techniques, and we map these into a lower dimension. So here we have mapped essentially all of the hydraulic head data. We have about 300 of these data, as well as stream flow data, measurements we do in rivers. We take all that information and we reduce that into lower dimensional space. And that is what we see here. So again, here, now we take our complex D and we map it into basically 2 dimensions. We notice that we get reasonable high representation of variance through there. We can also do that the same with the observation. And we notice here that the observation falls within this cloud. So that's good news. It means essentially that it is possible with my model to predict the observations. Notice that I'm not trying to do any inverse modeling here. I'm just trying to diagnose the problem whether if I would run any inverse modeling would actually make any sense. Namely, if that star would be over here, then obviously something is wrong with my prior model and then I have to do a revision. What one should not do is try to fix the problem and multiply, for example, certain parameters such that I end up over here. And we'll see in the next slide what would be a better situation or a better solution. I've often found in practice that falsification is a difficult to understand concept. Often we hear many different words used, such as validated, verified, calibrated, inverted, updated, etc. That's not what falsification means. Falsification means essentially that you had an initial hypothesis, which was your model complexity and your model uncertainty, and now you run it through a test. And so what falsification does, it makes that hypothesis is stronger if the hypothesis is not falsified. We can't say now that our prior model is the correct prior model. There are many still prior models that can also be not falsified. So falsification is just an initial stage that gives us some hope in moving forward that this is starting to make any sense. So if the model is falsified, however, then something needs to be done. What does not need to be done, we go to at length in the book, is what is called ad hoc modifications. Ad hoc modification means that sort of tweaking or fixing or fudging with this prior model such that I'll make sure that the model is not falsified. There's essentially a number of things that can happen. Either the model is falsified for a number of reasons. Either the model is too simple, or the model complexity is all right, but essentially the model uncertainty is too small, or it could be both. And of course, you do not know which one is happening. So we need to go through this revision with extreme care and really start to understand what is going on and why is this happening. One way of understanding a little bit better is to do sensitivity analysis, which is something that comes next in our workflow. So that is what sensitivity analysis is. So sensitivity analysis will be run on 2 variables. It will be run on the data variables as well as the prediction variables. And most importantly, we typically would do it first on the prediction variables because we'd like to understand what in the model variables is impacting most our prediction variables. That allows us to understand and focus mostly on the important model variables. If there are model variables that have absolutely no impact on the prediction, regardless of their uncertainty, then obviously we can discard those and we don't have to even worry about them. Then we do a sensitivity on the data variables, and then we particularly understand if there's any overlap between the sensitivity of model variables on both prediction and data. In particular, of course, we'd like to understand if there's any data variables or data that can be used to reduce uncertainty on those model variables have an importance in terms of predictions, making predictions. And that will allow us to fine-tune our uncertainty reduction methods a little bit better. The methods for sensitivity analysis that we use is global and Monte Carlo based sensitivity. So we're not looking here at a one-at-a-time sensitivity or screening methods because they don't allow to deal with the complexity and nonlinearity of our problems. So here would be a typical output for a sensitivity analysis. For example, in the Danish case, I'd like to understand what is affecting most data variable, which is here the hydraulic head and stream flow data. And so we notice here, somewhat surprisingly, in this sensitivity analysis, which is summarized as a Pareto chart, that the geological heterogeneity itself has no impact on the head variable, while the boundary conditions here, this is the recharge, meaning how much it rains, and the budget going into the model means the boundary condition, how much groundwater is flowing into my model, have the biggest impact. So if you would now start doing inverse modeling and adjusting the geological heterogeneity to match this data, you would be doing something fundamentally incorrect. We should be instead focusing on these two parameters. If you then look at the insensitivity on the forecasting part, for example, industrial pollution, then we notice that geological heterogeneity becomes very important. So this shows that, of course, that this head and stream flow data is not going to be able to fully reduce uncertainty on geological heterogeneity. However, there's some good news here, and it is that industrial pollution is also impacted by boundary conditions. So reducing uncertainty on head and stream flow on the boundary condition using head and stream flow data will help us in reducing uncertainty on an important prediction variable. Okay, so now we come to the design of uncertainty reduction. So we have identified important variables. We want to reduce uncertainty on them. So how do we do that? So here we typically run inverse modeling. But my experience with inverse modeling in general for real applications is it becomes very difficult to do, simply because we have to deal with a complex system with many uncertainties. So think about this groundwater problem. We have many uncertainties related to boundary conditions, geological interpretations, uncertainty related to geophysical data acquisition. In order to model stream flow and subsurface flow, we need to have stream flow models and multi-phase flow models. We also deal with reactive transport models, possibly biogeochemical models. We have to couple all these models into one model. And so each model can come with a box of uncertainties that is tremendous. So to think about now inverting all these model variables with all of the observations that are there, head data, stream flow data, SkyTEM data, borehole data, lithological data, test data, tracer data, etc., will be virtually impossible. Instead, in Bayesian Evidential Learning, we use a different strategy, and that is a strategy where we transform all nonlinear non-Gaussian problems to a linear Gaussian problem. And so here we have to use clever dimension reduction methods. Once we have done that, we predict with the linear Gaussian problem and back transform everything into the original problem. So what we try to avoid is traditional inverse modeling. The only thing that is going to be done is statistical calculation from the Monte Carlo. In other words, if I've done correctly my falsification problem, shown that my prior model is not falsified, have done a significant sensitivity study, which allows me to understand what is impacting what, then this the uncertainty reduction problem is a simple calculation and nothing else needs to be done. There are many methods of achieving this, and here I show one of the simplest one, which is called canonical correlation analysis. So remember that we have some high dimensional variable x and some high dimensional variable y. So for example, x could be my data variables and y could be my prediction variables. X could be my data variables, y could be my model variables, or vice versa. So this is some kind of high dimensional vector, which we now have reduced in dimension into fixed basis components and scalar parameters. So in the end, what I have now is a problem that involves just scalars. So this could be a million dimension, but this alpha k could just be a few hundred. So what I now like to understand is what is the relationship between alpha k and beta k? Is essentially a correlation that is existing that I can exploit? Because if a correlation exists between alpha k and beta k, then also a correlation exists between x and y. And so if I have observation, for example, of x, then I can reduce uncertainty on y. So to do that, we just look at some simple linear algebra, and we see that our x variable or high dimensional variable can be represented into a reduced dimensional space, which is these, for example, principal components. And same for the y, for the beta, we have these principal components. And so what we're looking for is to make linear combinations of principal components that lead me to this vector alpha c, called the canonical component, that correlates maximally with beta c. So that requires doing some transformation and finding some matrix alpha, such that if I transform the alpha into alpha c and the beta into beta c, I find that there is a maximal correlation between those two. So, and that correlation is called a canonical correlation. And I can find many such canonical correlations, as many actually as I have principal component vectors. But typically we'll be interested just in the first few. So let's do an example. Let's say I have all this information here. So what I've done here, I've taken this information, I've done dimension reduction, I've taken this information, done dimension reduction. So that leads me to basically scores. I get me to scores for alpha, and also I can transform this d ops into alpha. So now we have something that is, for example, 100 dimension plus 1, and here potentially say 50 dimensions or something like that. And so my problem now becomes about how do I correlate alpha to beta and then use the observations to reduce uncertainty on beta. So here we have another example. This is our uranium contamination example. So we'd like to predict this complex variable, which is uranium precipitation. And we have observation, for example, from tracer data from wells, conservative tracer, acetate tracers, many tracer information that is there. So same again, we turn all that information into coefficients, and we try to regress these coefficients. If we do canonical correlation analysis, then we notice here now that we can transform all that information into a variable alpha 1c and all the prediction variables into beta 1c, and I have my observations. And so now I notice that there is a correlation between the tracer data and the spatial distribution of uranium, and I've made a nice plot that shows that as terms of a linear correlation. So now once I have that, I can do dimension reduction, I can do uncertainty reduction simply by linear regression. Once I've done that linear regression, I have now reduced uncertainty on these coefficients. I plug that into my equation, and I get back through back transformation, I get back the posterior realizations of my concentration. Now you see that we get a much more narrow distribution due to the constraining of this tracer data. So here we see the same problem, but then or the same application, but then for the Great Danish groundwater system. So for example, we notice that the variable that has to relate to the stream flows has been updated. Its uncertainty has been reduced. And this is something we already expected through the sensitivity analysis. And we have a variable such as industrial pollution, but then for location C, that is in all our well locations, we see no update. And then again, that's something that is not a surprise because we have seen that in our sensitivity analysis. So now I'm ready to put everything into a single table, and there's a lot to say about this. I'm not going to go into this. We have, remember, our various locations. We have our various objectives. We put in the various scores, and we come up in the end with summing up all those scores in terms of a single score. And we see, for example, here that location D is a score that it seems to be a location that gives the highest score. In the book, we talk a lot about this because there's a lot more to say in terms of risk and return, because some of these objectives are risk objectives, others are return objectives, and so you can weigh risk versus return and do some kind of a trade-off analysis. So that's a very quick overview of Bayesian Evidential Learning. As you notice, it's not a method, it's a protocol. A protocol where you go through various stages, particularly model complexity and uncertainty, prior uncertainty, falsification, sensitivity analysis, uncertainty reduction. Each of these boxes can have different methods. You may use your favorite dimension reduction methods. Maybe you still want to do inverse modeling, but it's important that you go through these various stages, since these are somewhat logical stages that are based on the Bayesianism philosophy. So there's more material on the YouTube website, and there's also software available. I'd like to thank, of course, all my students from the Stanford Center for Resources Forecasting that have worked very hard on making this happen. You will find, indeed, on our website many repositories. One is related to how to run the Bell procedure for your own applications. So with that, I leave it, and I hope you have a very nice day.